Welcome to Science, to Sleep By, where the universe slows down just enough for wonder to find its way into your dreams. I'm your host, and tonight we ask a question that has followed humankind for centuries. Have we really found life on Mars? From ancient telescopes and fevered imagination, to robotic explorers sifting through crimson dust, we've carried this question in our collective heartbeat. Somewhere within those frozen valleys and dried riverbeds, could something even the smallest cell be waiting? Or have we been seeing only reflections of our own longing to not be alone? So, take a deep breath. Let the sound of space unfold softly around you. And as we begin, let's journey across millions of miles to the planet next door, and to the oldest mystery in science. Long before telescopes brought the heavens closer, ancient eyes turned to the night sky and saw a wandering red light moving against the steady backdrop of stars. It shimmered differently from the others, bold, restless, tinged with a hue that spoke of fire and conflict. The Romans called it Mars, after their god of war. The Babylonians saw Nergal, the deity of destruction. Across cultures and centuries, the planet's distinct crimson glow stirred stories of power and danger, an ember of mystery suspended in the cosmos. And though those myths faded with time, that allure, that gravitational pull of curiosity never truly left us. For generations, Mars has been the mirror where humanity projects its imagination. It's not just another planet. It's a canvas of possibility. To the naked eye, it feels almost close enough to touch. A neighbor glowing faintly in the dark. Unlike the gas giants or the distant icy worlds, Mars is tangible, reachable. It has mountains, valleys, and storms. It rotates on its axis like Earth, has polar caps that grow and shrink with the seasons, and landscapes that seem eerily familiar. To the human mind, it feels like a place where life could have been, or maybe still is, quietly waiting beneath the dust. When the first telescopes were turned toward Mars in the 17th century, astronomers began to see dark patches and light regions. They charted what they thought were continents and seas, as though Mars were a living twin to Earth. The imagination of humanity stretched even further when Italian astronomer Giovanni Schiaparelli described seeing canali channels that crisscrossed the Martian surface. The term was mistranslated in English as canals, and suddenly, the world was abuzz with the idea that intelligent life might be building structures on another planet. People envisioned vast networks of waterways constructed by a dying civilization struggling to survive on a desert world. That idea, romantic and speculative, captured something deep within us. The hope that we are not alone, that somewhere out there, minds like ours exist, facing the same cosmic loneliness. Science fiction was born from that spark. Writers like H.G. Wells imagined war between worlds, while others pictured peaceful Martians looking up at our blue planet as curiously as we looked at theirs. Mars became more than a dot of light. It became a reflection of ourselves, an echo of our fears, our ambitions, and our longing for connection. As technology advanced, so did our questions. When we sent the first spacecraft toward Mars in the 1960s, we were not just exploring, we were fulfilling a promise that had been whispered for centuries. The Mariner missions offered the first close-up images, barren, cratered, silent. The fantasy of bustling alien cities gave way to the reality of a frozen desert. And yet, even that emptiness did not extinguish our fascination. If anything, it deepened it. The red planet was not alive with civilizations, but perhaps, somewhere within that quiet terrain, something smaller, bacterial, mobile, might still persist. Life, but in a form we had yet to fully imagine. There's something poetic in how our perception of Mars has evolved. At first, it was a god fierce and untouchable. Then it became a mirror of our imagination, filled with canals and creatures. Now, it stands as a riddle of science, cold, silent, and yet brimming with questions. Its mountains rise taller than any on Earth, and its canyons stretch wider than anything carved by our rivers. Dust storms engulf the entire planet for months at a time, whispering across dunes that have lain undisturbed for millennia. Each gust, each ripple of sand, feels like a page in a story we're only beginning to read, Scientists have long wondered why Mars feels so familiar. Part of the answer lies in its history. Billions of years ago, Mars may have been a warmer, wetter world. Ancient riverbeds and lake basins suggest that water once flowed across its surface, a key ingredient for life as we know it. If that's true, then Mars was not always a frozen wasteland. It may once have had blue skies, liquid oceans, and a climate capable of nurturing something living. Somewhere in that ancient landscape, perhaps microbes once thrived, sheltered beneath the warmth of a young sun. That possibility continues to draw us closer. Every mission we send is another chapter in our search for that answer. The allure of Mars isn't just scientific. It's deeply emotional. It's a reflection of humanity's need to seek meaning beyond ourselves. Each rover's tire track, each orbiting probe, is a declaration of curiosity, a reminder that we are a species driven by wonder. Even when faced with endless silence, Mars is also a test of endurance, both for our machines and our imagination. It's a world that challenges us with extremes, freezing temperatures that can drop to -100 degrees Fahrenheit, thin air filled with carbon dioxide, and radiation that seeps through the atmosphere like an invisible wind, yet we persist. We design robots to roll across its dusty plains, to dig into its soil, to sniff for traces of past life. Each grain of Martian dust analyzed in a lab back on Earth carries a whisper of potential, a clue that might rewrite our understanding of biology. In many ways, our journey to Mars mirrors our journey within. It's the story of curiosity turning into courage, of questions transforming into exploration. The red planet, with its mysterious charm and austere beauty, calls to something primal, the same instinct that led ancient humans to cross oceans and mountains, to look at a distant horizon and wonder what lies beyond. Even now, when we gaze at Mars through telescopes or images from rovers, we feel that tug, not just a scientific one, but a spiritual one. It's as if Mars exists both out there in the void and within the quiet corners of our own imagination. Its red glow reminds us that the universe is vast and alive with possibility. It whispers that even amid the silence of space, there may still be echoes of life, faint but enduring, waiting for the moment when we finally listen closely enough to hear Themis. The 19th century unfolded. Humanity's gaze toward Mars became something far deeper than simple observation. It was an age of optimism, a period when science and imagination intertwined in a delicate dance. The Industrial Revolution had reshaped the world, telescopes had grown sharper, and minds hungry for discovery began to believe that the universe might be teeming with neighbors. And at the center of those dreams stood Mars, bright, red, and mysterious. Through the lenses of early astronomers, the red planet appeared as a world both alien and familiar, a place that seemed to mirror the landscapes of Earth, yet spoke in whispers of something more. 1877. Italian astronomer Giovanni Schiaparelli turned his telescope toward Mars during a rare opposition. When the planet came closer to Earth than it had in centuries, he noted a network of dark, thread-like markings that seemed to trace across the planet's surface. He called them canali, meaning channels in Italian. The word was innocent enough, a scientific term to describe the dark streaks he observed. But when translated into English, canali became canals, and that single linguistic twist ignited a wildfire of speculation. Canals were artificial by nature, built by intelligent beings. The idea that someone or something on Mars had carved massive waterways across its surface was too irresistible for the public to ignore. In America, astronomer Percival Lowell became one of the most passionate defenders of this vision. From his observatory in Flagstaff, Arizona, he spent years meticulously mapping what he believes to be an enormous network of canals built by an advanced Martian civilization. He wrote vivid accounts describing a dying planet, where intelligent beings had constructed massive irrigation systems to channel water from the polar caps down to the arid equatorial plains. In Lowell's eyes, Mars was not just a planet, but a story, a tragic one, filled with ingenuity, perseverance, and the slow fading of a civilization clinging to survival under a weakening sun. Lowell's writings captured the public's imagination in ways that pure science rarely could. Newspapers printed illustrations of the Martian canals. Magazines speculated about what these alien engineers might look like. And lecture halls filled with curious minds, eager to glimpse the possible neighbors living just 35 million miles away. For the first time, the concept of extraterrestrial life had moved from the fringes of mythology into the realm of scientific conversation. It was no longer a matter of gods or spirits, but of beings, intelligent, rational, perhaps even moral, living under the same cosmic science fiction. Still in its infancy, blossomed in the fertile soil of these ideas. Writers like H.G. Wells and Edgar Rice Burroughs transformed Mars into a stage for human dreams and fears. In 1898, Wells published The War of the Worlds, a chilling tale of Martian invaders descending upon Earth, bringing death and devastation. Beneath its surface, the story reflected a reversal of colonial narratives. It asked readers to imagine what it would feel like to be on the receiving end of superior technology and ambition. The Martians were no longer imagined as peaceful philosophers gazing up at our blue world, but as desperate conquerors, seeking to claim the resources their dying planet could no longer provide. Meanwhile, in Burroughs's A Princess of Mars, published in 1912, the Red Planet became a place of adventure, heroism, and romance. His Mars, or Barsoom, as he called it, was populated by warrior tribes, strange creatures, and grand kingdoms. The tone was fantastical, but the allure was undeniable. Mars, whether hostile or noble, had captured the human heart. It became not merely a celestial object, but a reflection of the human condition itself, a mirror for our hopes, our fears, and our relentless curiosity. The scientific community, however, began to wrestle with doubt. As telescope technology improved, the canals that Lowell so passionately defended began to vanish from clearer, sharper images. Astronomers such as E.M. Antoniadi, observing from France, reported that the canals were optical illusions, tricks of light and perception caused by the human eye's tendency to connect faint markings into lines. Mars, it seemed, was not etched with grand waterways, but pocked with natural features, craters, dunes, and ridges. Still, the myth of the Martian canals refused to die easily. It had embedded itself in the cultural imagination, too deeply woven into the collective psyche to be dismissed by mere facts, even as evidence against the canals mounted. The dream of Martian life adapted and endured. Scientists proposed new theories. Perhaps Mars harbored plant life, covering its surface with seasonal tints of green and red. Perhaps microscopic organisms thrived beneath its dusty soil, hidden from view. The fascination with Mars had shifted from a grand civilization to smaller, subtler forms of life, a reflection of the growing complexity of biology and the humility of modern science. The 20th century dawned with a new kind of wonder, one grounded in possibility rather than fantasy. The canals faded, but the longing remained. Telescopic observations showed that Mars had polar ice caps that waxed and waned with the seasons, and this simple observation reignited hope. Water, after all, was the cradle of life on Earth. If Mars had once known liquid water, perhaps life could have found a foothold there as well. In schools and lecture halls across the United States, children grew up dreaming of the Red Planet. Mars became a symbol of exploration and destiny, a future frontier for humanity to conquer. The myths of Martian civilizations evolved into questions about microbial survival, planetary evolution, and the boundaries of biology itself. The early dreams of life on Mars had begun as poetry and fantasy, but they left behind something enduring, a scientific curiosity that would drive generations of explorers, engineers, and dreamers to reach across space in search of truth. What began as a mistranslated word and a few blurry telescope sketches had sparked one of the most profound quests in human history. The story of Martian life moved from mythology to speculation to scientific investigation. It became a bridge between imagination and evidence, between the yearning heart and the rational mind. Even as the old vision of canals faded into history, it left behind a legacy of wonder that continued to shape how we see the universe and our place within it as the 20th century advanced and telescopes reached their limits. Humanity's curiosity demanded a closer look. The shimmering red dot that had captivated dreamers and scientists alike for centuries could no longer be understood from afar. We had imagined canals and civilizations, but the time had come for truth to replace speculation. The dawn of the space age offered what poets and astronomers had only dreamed of: the ability to cross the gulf between worlds. And with that power came the first wave of explorers, not of flesh and blood, but of metal, circuits, and silence. They would become our eyes, our hands, and our witnesses on Mars. The 1960 seconds were an age of competition and wonder. As the Cold War tightened its grip on Earth, the race for the heavens became a reflection of human ambition itself. The United States and the Soviet Union turned their gaze toward Mars, each determined to be the first to touch its surface, to unlock its secrets. In 1960, the Soviets launched the first attempts, but Mars was not a forgiving destination. Every early mission met with failure. Rockets exploded, signals vanished, and spacecraft were lost in the dark. Mars, it seemed, was guarding its mysteries well. Then, in 1965, NASA's Mariner 4 changed everything. It became the first successful spacecraft to fly by Mars, capturing 22 grainy images that forever altered humanity's understanding of the red planet. The pictures it sent back were not the lush landscapes that many had hoped for, but instead revealed a world scarred by craters, ancient and desolate. The surface appeared eerily similar to the moon, barren, dry, and silent. For many, it was a moment of disappointment. The dream of a living, breathing Mars, filled with vegetation and canals, seemed to dissolve in those gray, dusty frames. But for science, it was a beginning, not an end. The mystery had simply deepened. In the following decade, Mariner 6 and 7 provided even more detailed observations, showing the planet's thin atmosphere and temperatures far below freezing. Then came Mariner 9 in 1971, the first spacecraft to orbit another planet. As it arrived, a massive dust storm enveloped the entire globe, hiding the surface beneath swirling clouds of iron-rich particles. For weeks, Mariner 9 waited patiently until the storm began to settle, revealing a breathtaking sight: enormous volcanoes, colossal canyons, and dried riverbeds stretching for hundreds of miles. Olympus Mons, the largest volcano in the solar system, towered nearly 3 times higher than Mount Everest. The Great Canyon, Valles Marineris, carved into the Martian crust, was vast enough to stretch from New York to Los Angeles. These discoveries reignited hope. Mars was not lifeless after all. It was a planet with a dynamic past, shaped by water, fire, and time. By the mid-1970s, NASA prepared for a bold new step. Not just to see Mars, but to touch it. The Viking program would mark humanity's first attempt to land on the red planet and search directly for signs of life. Viking 1 and Viking 2, launched in 1975, carried with them both orbiters and landers, each designed to work in tandem. When Viking 1 touched down in 1976, it became the first spacecraft to successfully operate on the Martian surface. The first color photographs it sent back were haunting and beautiful. An alien horizon bathed in pink light, scattered rocks casting soft shadows under a pale salmon sky. For the first time in history, humans saw the surface of Mars as it truly was. Not through myth or imagination, but through the lens of a machine that had traveled millions of miles to stand in our place. The Viking landers were more than cameras. They were miniature laboratories, equipped to test for life. They scooped soil samples and ran experiments designed to detect biological activity. For a fleeting moment, it seemed as though they might have found it. One of Viking's tests produced results that hinted at metabolic processes, reactions that looked remarkably similar to what living microbes might create. The excitement spread quickly. Perhaps, after centuries of searching, we had finally discovered life beyond Earth. But as the results were analyzed, the evidence grew murky. Other experiments found no organic molecules, no definitive proof. The apparent signs of metabolism could have been caused by chemical reactions rather than biology. It was a scientific puzzle that still lingers today, suspended between possibility and doubt. Despite the uncertainty, the Viking missions were monumental achievements. They transformed Mars from a distant dream into a tangible world of rocks, soil, and dust. They measured its atmosphere, analyzed its chemistry, and mapped its surface in astonishing detail. For decades, the data they collected remained the foundation of Martian research. They showed us a planet both familiar and alien, one that bore traces of ancient rivers and floodplains, suggesting that billions of years ago, Mars might have been warmer and wetter. If it had once possessed oceans or lakes, then perhaps, in those vanished waters, life could have taken root. After Viking, a long silence followed. The 1980s and early 1990s became known as the Mars drought. Budget cuts, technical failures, and shifting political priorities slowed exploration to a halt. But Mars continued to whisper its silent invitation, and humanity listened. When NASA returned in 1997 with the Mars Pathfinder mission, the world watched in collective awe as the small Sojourner rover rolled across the dusty surface. It was the first robot to move freely on another planet, its wheels pressing faint tracks into red soil that had not been disturbed for eons. Unlike the static Viking landers, Sojourner was mobile, curious, alive in its own mechanical way. It analyzed rocks, sent back vivid images, and reminded humanity that exploration was far from over. From that moment, Mars became an ongoing conversation between Earth and another world. Every new mission, from the twin rovers Spirit and Opportunity to the orbiters that mapped mineral deposits and weather patterns, built upon the legacy of those first robotic pioneers. They revealed evidence of ancient river deltas, minerals formed in water, and traces of organic molecules that hinted at chemistry once suited for life. Each new discovery layered complexity onto the question that had driven centuries of wonder, not whether Mars had life now, but whether it ever had life at all. The story of Mars's robotic explorers is not just one of machines and data. It is a story of persistence, of human imagination made tangible through technology. Each lander, each rover carried with it the echoes of those early dreams, the canals, the civilizations, the longing to know. And though these explorers were silent emissaries, they spoke in a language more profound than words, sending whispers of dust, light, and possibility back across the void in the icy emptiness of Antarctica, where wind scours the surface and silence reigns eternal. A strange stone lay hidden beneath the snow for thousands of years. It was small, no larger than a human hand, but within its rough surface, it carried a story billions of years in the making. This meteorite, later known as LH84001, would one day ignite one of the most extraordinary debates in modern science. Had we, at last, found proof of life beyond Earth? It began in December 1984, when a team of American scientists searching for meteorite stumbled upon a dark, oddly textured rock in the Allen Hills region of Antarctica. The meteorite was catalogued simply as Allen Hills 84001, a name that, at the time, seemed to promise little more than another entry in a growing collection of extraterrestrial fragments. But this one was different. As scientists examined it more closely, they realized it wasn't just a random piece of space debris. It was a messenger, a relic from Mars itself. Trapped inside its mineral structure were chemical fingerprints that matched the Martian atmosphere, as later confirmed by data from the Viking landers. The rock had been blasted off Mars millions of years ago, likely by a massive asteroid impact, and had drifted through the cold void of space before falling to Earth roughly 13,000 years ago. Over a decade, LH84001 sat quietly in a NASA collection, studied but not fully understood. It wasn't until the mid-1990s that the rock's true significance began to emerge. A group of researchers led by Dr. David McKay at NASA's Johnson Space Center made a startling discovery. Inside the meteorite structure were microscopic features that, under powerful electron microscopes, resembled fossilized bacteria, tiny, worm-like shapes embedded in the mineral matrix. Alongside them were traces of organic molecules and magnetite crystals that, on Earth, are typically produced by certain types of microbes. To McKay's team, these signs pointed to one extraordinary possibility, that the meteorite contained evidence of ancient Martian life. When NASA announced the findings in August 1996, the world reacted with a mixture of awe, disbelief, and wonder. The story exploded across headlines. Life on Mars became a phrase that echoed from television screens to classroom discussions. For the first time in history, humanity faced the possibility that life might not be unique to Earth. The image of those tiny fossil-like shapes became iconic. Magnified photographs showing curved, thread-like forms that looked remarkably biological. In those delicate contours, many saw not just ancient microbes, but the beginning of an answer to one of humanity's oldest questions. Even the highest levels of government took notice. Then President Bill Clinton addressed the nation from the White House lawn, calling the discovery a moment that speaks to the possibility of life beyond our planet. He spoke of a future where children might grow up knowing that humanity was not alone in the universe. It was a moment that blended science with something almost spiritual. The sense that the boundaries of our world had suddenly expanded. But science, by its very nature, demands skepticism. Almost as quickly as excitement spread, so too did debate. Other researchers began scrutinizing the evidence, questioning whether the features in LH84001 truly required life to explain them. Could the magnetite crystals have formed through geological processes rather than biological ones? Could the organic molecules have been created by chemical reactions in the rock itself, or even by contamination after it landed on Earth? The lines between biology and geology, between life and chemistry, began to blur in ways that challenged even the most careful observers. Laboratories around the world conducted experiments to replicate the structures seen in the meteorite. Some managed to produce similar shapes and mineral patterns without any involvement of living organisms, suggesting that non-biological processes might indeed explain the evidence. The controversy grew fierce, not because scientists wanted to disprove the idea of Martian life, but because the implications were too profound to accept without absolute certainty. To claim life had existed on Mars required evidence that could withstand every doubt, every challenge, every shadow of uncertainty. Yet even as skepticism mounted, the meteorite refused to fade into obscurity. It had reignited humanity's imagination. The idea that microscopic life could have once thrived on a neighboring planet captured something deeply emotional, a sense of connection that reached beyond the boundaries of Earth. Artists painted visions of Martian microbes glimmering under ancient sunlight. Writers and filmmakers returned to the red planet with renewed fascination. Scientists, too, found themselves inspired. The meteorite had reminded them that Mars was not a sterile world, but a dynamic one, a planet whose history might yet hold the fingerprints of biology. The impact of LH84001 extended far beyond its own controversy. It reshaped how space agencies approached the search for life. NASA began to focus not merely on finding organisms, but on understanding the conditions that could support them. Missions like Mars Global Surveyor, launched in 1996, and later Mars Odyssey, and the Rover's Spirit and Opportunity, were designed to look for water, carbon, and other ingredients essential for life. The very question of habitability, what makes a world capable of supporting life, became central to planetary science. The meteorite had not provided an answer, but it had given scientists a new way to ask the question. At the same time, LH84001 challenged humanity's perception of life itself. If microbial life could have existed on Mars billions of years ago, perhaps life was not rare at all. Perhaps it was the rule, not the exception. Maybe life did not need oceans and forests to flourish. Maybe it could survive in the frozen soil of another planet, or in the depths of space, carried from world to world on fragments of rock, like the one that fell in Antarctica. This idea, known as panspermia, gained renewed attention. It suggested that life might travel across the universe, seeded by impacts and cosmic dust. making the boundary between planets less rigid than we once believed it. Decades later, the debate over LH8401 remains unresolved. The meteorite still sits in NASA's collection, carefully preserved, studied with newer and more sophisticated instruments each year. No definitive conclusion has been reached, and perhaps that uncertainty is what makes it so powerful. It stands as a symbol of both science and mystery, of our unending search for answers in a universe that rarely gives them easily. It reminds us that discovery is not always about proof, but about pursuit. The relentless human desire to know, to question, and to look beyond the world we call home. As humanity's exploration of Mars deepened, so, too, did the complexity of its mysteries. The red planet continued to whisper secrets through thin air and scattered dust, offering glimpses of potential life, only to retreat into ambiguity. It became a world of paradoxes where every discovery seemed to both confirm and contradict our greatest hopes. In laboratories and mission control rooms, scientists began to wrestle with the subtle dance between biology and chemistry, between living signals and lifeless imitations. Were the traces of methane, organics, and other tantalizing markers truly signs of life? Or were they the echoes of purely geological processes, chemical reactions playing tricks on our expectations? The first great clue came in the form of methane, a simple molecule, yet one with profound implications. On Earth, the majority of methane is produced by living organisms, from microbial activity deep underground to the metabolic processes of animals. Detecting methane on Mars, therefore, could suggest something biological, however small or ancient. In 2003, telescopic observations from Earth revealed faint but significant traces of methane in the Martian atmosphere. This finding electrified the scientific community. Methane should not last long in the thin, oxidizing air of Mars. It should be destroyed by sunlight within a few hundred years. Its very presence meant it had to be replenished. Something was actively producing it, or releasing it, even now. Soon after, orbiters like the European Space Agency's Mars Express confirmed localized plumes of methane, concentrated in specific regions such as Gale Crater and Syrtis Major. Later, NASA's Curiosity rover, landing in Gale Crater in 2012, detected fluctuating levels of methane as it traversed the ancient terrain. The readings varied over time, sometimes nearly disappearing, sometimes spiking dramatically as though Mars were breathing in slow, hidden rhythms. To many, this pattern felt alive, like a pulse in the planet's atmosphere. But nature, even without life, can mimic vitality. Geological processes, such as the interaction of water with certain rocks, can also produce methane through purely chemical means. The mystery deepened. If not biology, then what was stirring the gas beneath the Martian surface? The search for organic molecules, the building blocks of life, added another layer to the intrigue. In 2014, the Curiosity rover made a groundbreaking discovery. It had detected complex organic compounds preserved in ancient rocks billions of years old. These molecules, composed of carbon, hydrogen, and other elements, were the same ingredients found in all known life forms. The rocks in which they were found appeared to have formed in a lake environment, suggesting that Mars had once hosted conditions remarkably similar to those on early Earth. Yet, while organic molecules are essential for life, they do not necessarily indicate life's presence. They can also arise through non-biological reactions, formed by sunlight, volcanic activity, or the delivery of carbon-rich meteorites. The line between alive and not alive blurred once again, leaving scientists suspended in a state of fascinated uncertainty. One of the more haunting aspects of the search came from the Viking missions decades earlier. In 1976, Viking's onboard experiments had seemed to detect possible signs of metabolism in Martian soil samples, but without the discovery of organic molecules. The findings were dismissed as chemical artifacts. When Curiosity finally found those organics, it forced scientists to look back at the Viking data with renewed interest. Had the landers of the 1970s already glimpsed something living, but been too early to understand what they'd found? Or were these echoes of abiotic processes that had fooled even the most advanced instruments of their time? The question lingered like a shadow that stretched across decades. The discovery of recurring slope-linear dark streaks that appear seasonally on Martian hillsides further complicated the story. These streaks, first noticed by the Mars Reconnaissance Orbiter in the 2010s, seemed to flow and fade with the changing seasons, as if water, the essence of life, might still trickle beneath the surface. For years, scientists debated whether these features represented briny liquid water or merely the movement of dry dust. The possibility of even transient water ignited hope, for wherever water exists, life as we know it has a chance. But as analysis continued, newer data suggested the streaks could be caused by shifting sand or surface salts reacting with humidity, not true flowing water. Again, what had looked like a sign of life turned out to be something colder and more mechanical, shaped not by biology, but by chemistry and physics. As missions grew more sophisticated, the boundary between evidence and illusion only grew thinner. NASA's Perseverance rover, which landed in Jezero crater in 2021, carried instruments capable of analyzing rock samples in unprecedented detail. Jezero was once home to an ancient lake and river delta, environments that could have sheltered microbial life billions of years ago. Early results hinted at complex organic chemistry locked within Martian minerals, alongside traces of carbon isotopes that, on Earth, are often associated with biological activity. Yet even this tantalizing evidence came with a caveat. The same chemical signatures could also arise from volcanic gases interacting with sunlight and minerals. Every clue seemed to contain both promise and doubt. Like a riddle written in stone, the tension between biology and geology became the central theme of Mars exploration. Scientists began to speak not of proof, but of biosignatures, patterns or molecules that could indicate life, but were not definitive. The problem was that Mars, unlike Earth, had long ago lost its magnetic field and much of its atmosphere, leaving it vulnerable to cosmic radiation. Any traces of ancient biology near the surface would have been erased over eons. If life ever existed there, it might now lie deep underground, preserved in frozen aquifers or buried rock layers beyond the reach of current rovers. The more we searched, the more Mars seemed to retreat into secrecy, as if guarding its truth beneath miles of red dust. Even methane itself, once hailed as the key to life, grew increasingly mysterious. In 2019, the European Trace Gas Orbiter found almost no methane at all, contradicting both curiosities and Earth-based observations. The contradiction forced scientists to confront the possibility that methane was being destroyed faster than expected, or that it was released only in fleeting, localized bursts, like breath exhaled and immediately consumed by chemical reactions in the thin air. The data didn't fit neatly into either a biological or a geological explanation. It seemed Mars was caught between two stories, one of chemistry, one of life, and refused to tell us which was true. What emerged from all this was a deeper, more nuanced understanding of what life means. Perhaps we had been searching with the wrong expectations, looking for the familiar instead of the possible. Life on Mars, if it ever existed, might not look like anything on Earth. It could be built from different elements, operate under different rules, or leave behind traces so subtle we've yet to recognize them. Each rover, each orbiter, each probe added another layer of knowledge, not of certainty, but of wonder. Mars had become a planet of almosts. Almost alive, almost revealing, almost understood. In the quiet tension between chemistry and biology, the red planet held its silence, inviting us to listen more carefully, to look more closely, to question not only what life is, but how it chooses to reveal itself. When NASA's Perseverance rover touched down on the Martian surface in February 2021, it carried with it the weight of generations of questions. The landing itself was a triumph, a ballet of precision and courage, a moment when human ingenuity met the endless red silence of another world. As Perseverance descended through the thin, dusty atmosphere, its cameras recorded every trembling second of its 7 minutes of terror, the perilous stretch between entering Mars' atmosphere and touching the ground. When the rover's wheels finally settled on the rock-strewn floor of Jezero crater, cheers erupted in mission control. Humanity had once again reached across space to place a hand upon the unknown. But Perseverance's mission was more than exploration, it was an attempt to answer a question older than civilization itself. Had Mars once harbored life? Jezero crater was not chosen by chance. From orbit, scientists had seen evidence that it was once home to a vast lake, fed by ancient rivers that carved a delta into the crater's rim. Billions of years ago, when Mars was warmer and wetter, Jezero may have been a cradle of microbial life. The sediments that once settled at the bottom of its lakebed could still hold the chemical and fossilized traces of those vanished organisms. Perseverance was built to search for those traces to become the most sophisticated geobiologist ever sent beyond Earth. The rover's landing site, a gently sloping expanse of rock and dust, is more than an alien plane. It's a frozen moment in planetary history. Every boulder, every ripple of sand tells part of a story written in water and time. The rocks that Perseverance studies were once sediments that sank in still water, compacted by eons into layered stone. Within those layers may lie organic molecules, minerals shaped by liquid chemistry, and the faintest whispers of ancient biology. With its suite of advanced instruments, Perseverance can peer into those stones with laser precision, vaporizing tiny samples to analyze their composition, searching for patterns that suggest something once lived there. Perseverance's mission goes beyond analysis, it is about collection and preservation. For the first time in history, a rover is gathering physical samples of Martian rock and soil to one day be returned to Earth. Inside its titanium tubes, the rover seals away pieces of the planet's surface, each one carefully catalogued and stored for future scientists to study in terrestrial laboratories. These samples may one day reveal whether Mars ever nurtured microbial life, whether its chemistry once danced to the same rhythms that brought life to Earth. The plan for their eventual retrieval involves a daring collaboration between NASA and the European Space Agency, a complex ballet of orbiters and landers that will, in coming years, attempt the first interplanetary delivery of samples back home. It is an undertaking unlike any before, one that could answer humanity's most enduring cosmic question. The Perseverance rover itself is an evolution of everything learned from its predecessors. Its body carries the heritage of spirit, opportunity, and curiosity, each of which taught scientists how to survive the unforgiving terrain of Mars. But Perseverance represents a new chapter, one focused less on survival and more on discovery. Its instruments are designed not just to detect the presence of organic molecules, but to distinguish between those formed by life and those shaped by geology. Its cameras, the most advanced ever sent to another planet, capture the Martian landscape in breathtaking clarity, revealing a world that feels almost familiar: cliffs, riverbeds, wind-carved dunes, and the remnants of a world that once knew rain. Alongside Perseverance came a companion, a small helicopter named Ingenuity. At first, Ingenuity's mission was merely experimental to see if flight was even possible in the thin Martian atmosphere, which has less than 1% of the density of Earth's air. Yet the tiny craft exceeded every expectation. It flew again and again, soaring over alien terrain, scouting routes for the rover, and proving that the skies of Mars could indeed be conquered. Each of its flights became a symbol of human persistence, a quiet echo of the same curiosity that once lifted hot air balloons into the skies of Earth. Ingenuity was not designed to search for life, yet in its graceful arcs above the crater, it became a metaphor for it, for the boundless drive to explore and to endure. As Perseverance explored Jezero, it found clues that spoke of Mars' watery past. The delta deposits showed evidence of clay and carbonate minerals, both of which form in the presence of water and are capable of trapping organic compounds. The rover's instruments detected complex carbon molecules within those ancient rocks, molecules that, while not proof of life, hinted at chemical processes that could have supported it. The patterns in the rock suggested cycles of wet and dry conditions, much like those that shaped Earth's early microbial ecosystems. Scientists began to piece together a vision of Jezero as it might once have been a blue lake beneath a pale orange sky, bordered by river deltas where sediment and nutrients gathered, where sunlight and water mingled to create a chemistry that could have sparked life. But the search for life on Mars has never been simple. Each discovery opens the door to new uncertainty. Were the organics found by perseverance, created by biological activity, or by non-living chemical reactions fueled by volcanic gases and ultraviolet radiation? Were the carbon isotopes that seem suggestive of life truly biological in origin, or the result of ancient atmospheric processes? Every new piece of data had two faces, one whispering of life, the other of mere chemistry. Mars continued to play its silent game of ambiguity, its secrets buried just beneath the surface. Beyond science, Perseverance also carried something profoundly human: messages, names, and hope. Hidden on its body are the names of nearly 11 million people from Earth, etched into silicon chips, a symbolic gesture of connection between our world and the one it seeks to understand. On its deck is a plaque honoring the healthcare workers who faced the global pandemic that raged while the rover was being built, a reminder that exploration, even in the vastness of space, remains rooted in the human spirit. The mission's very name, Perseverance, captures the essence of what it means to search for life on Mars. It is the story of persistence against doubt, of curiosity against silence, of small steps on distant soil, echoing the ancient human impulse to know where we come from and what other forms life might take in the universe. Each drill sample, each panoramic image, each quiet wheel mark left in the Martian dust is a continuation of that story. It is the culmination of centuries of wandering, from Schiaparelli's canals to Lowell's civilizations, from Vikings' experiments to the Meteorite LH84001, all leading to this single robot, standing in a dry crater that was once a lake, looking for the ghosts of ancient microbes. And while Perseverance continues to climb ridges and explore the desiccated river delta, it carries within its instruments a question that humanity has whispered since it first looked up at the stars. A question written not only in science, but in the quiet poetry of discovery, in the endless persistence of the human soul to seek, to reach, and to remember. For decades, the search for life on Mars has been a robotic endeavor. Machines like Spirit, Opportunity, Curiosity, and Perseverance have acted as our distant hands and eyes, sending back whispers from a silent world. But now, as technology advances and ambitions expand, humanity stands on the edge of a transformation. The dream that once belonged to science fiction is inching toward reality, sending humans, not robots, to the red planet. The difference between a rover's lens and a human gaze is immeasurable. A robot can scan, analyze, and transmit, but it cannot feel the gravity of standing beneath a salmon-colored sky, or sense the fragile stillness of a planet that might once have lived. That moment, when human boots touch Martian soil, will not just be an act of exploration. It will be a profound encounter with history, science, and existence itself. NASA, SpaceX, and international agencies have all begun to outline the framework for a crewed mission to Mars in the coming decades. These missions would require solving problems of enormous complexity, propulsion systems powerful enough to make the journey, habitats capable of shielding astronauts from radiation, and life support technologies that can sustain them through years of isolation. Every detail must account for a distance so vast that communication delays can stretch up to 22 minutes each way. There will be no immediate rescue, no quick return, and no easy answers. Yet, despite these challenges, the idea of humans walking on Mars continues to inspire the most daring minds of our generation. The Artemis program, designed to return astronauts to the moon in preparation for Mars, is part of this great stepping stone strategy. The moon serves as both a testbed and a proving ground, allowing scientists to develop systems for long-duration survival away from Earth. Mars is far less forgiving than the lunar surface. Its atmosphere is thin and unbreathable, its temperatures plummet to extremes, and the radiation from the sun is relentless. A human mission there demands a new way of thinking, not just about engineering, but about psychology, biology, and endurance. To live on Mars, humans will have to become adaptable in ways that redefine the limits of the species. Within NASA's Johnson Space Center, simulated habitats and isolation chambers already prepare astronauts for the mental and physical strain of such missions. These experiments mimic not just the physical constraints, but also the emotional solitude that comes with being millions of miles from home. Astronauts living in these analog Mars habitats face delayed communications, limited resources, and the same monotony that a real mission would entail. They learn how to make decisions independently, to rely on their crew, and to confront the eerie quiet that comes from being cut off from Earth's immediate presence. Mars, with its rust-colored plains and empty horizons, will test not only scientific skill, but human resilience, the ability to remain calm, rational, and hopeful in the face of cosmic isolation. For all its challenges, the human presence on Mars holds unmatched scientific promise. A geologist kneeling beside a Martian rock could, in a single glance, interpret subtleties that would take a rover weeks to decode. The dexterity of human hands, the intuition of human judgment. These are tools no machine can replicate. Humans could collect, analyze, and cross-examine samples on site, following threads of evidence that only emerge through spontaneous thought and experience. In the search for life, this flexibility could make the difference between a vague signal and a definitive discovery. A single microscopic fossil, unearthed by human hands beneath a Martian ridge, would answer one of humanity's oldest questions in an instant. The journey to Mars will also reshape our understanding of what it means to explore. Unlike the Apollo missions, which lasted mere days, a Mars mission would require years. The journey there alone could take 6 to 9 months, followed by extended habitation before the return window opens. Every system aboard must be self-sufficient, from oxygen production and food growth to medical care and waste recycling. NASA's experiments with growing plants in space are not just exercises in sustainability. They are blueprints for how to turn a barren world into a livable one. The green sprout of lettuce aboard the International Space Station, bathed in artificial light, is a small symbol of what may one day grow in Martian soil. SpaceX's Starship project represents one of the boldest attempts to make interplanetary travel a recurring reality. Elon Musk envisions fleets of reusable spacecraft carrying supplies, habitats, and eventually settlers to Mars. His dream is not just a single mission, but a sustained human presence, a city under a red sky. Though the timeline remains uncertain, the ambition reflects a profound truth. Humanity's relationship with Mars has shifted from imagination to intention. The red planet is no longer just a distant point of light. It is becoming a destination. Yet even as the plans take shape, the psychological frontier remains the hardest to cross. To leave Earth for Mars is to abandon everything familiar. The rhythm of oceans, the pull of gravity, the blue of the sky. Astronauts will live under a dome, surrounded by machines, with the constant awareness that outside lies a landscape both breathtaking and lethal. The faint hum of life support systems will replace the sounds of wind and birds. Messages from loved ones will arrive minutes late, reminders of a world that spins on without them. It is a journey not just of distance, but of emotion, identity, and belonging. Scientists and psychologists alike study how the human mind copes with such prolonged separation, because on Mars, loneliness itself will be an environment to navigate. When the first human steps onto Martian soil, it will also mark the beginning of an ethical conversation. What responsibilities will we carry toward this new world? If microbial life still exists beneath its surface, hidden in briny streaks or buried ice, how do we ensure that our presence does not contaminate it? Planetary protection becomes not only a scientific requirement, but a moral one. To find life, we must first ensure that we do not destroy it. Every tool, every sample, every footprint will matter. The boundary between discovery and disturbance will be thin, fragile, and deeply significant. As plans advance, the idea of Martian habitats is being refined through imagination and engineering. Concepts range from inflatable domes buried beneath regolith to 3D printed dwellings built from Martian dust itself. Radiation shielding lava tubes, vast tunnels carved by ancient volcanic flows, may one day become underground sanctuaries for explorers. Engineers dream of systems where water is extracted from the soil, oxygen from carbon dioxide, and energy from the relentless Martian sunlight. The architecture of survival is being drawn one line at a time, guided by both necessity and wonder. While machines can record data, humans will experience Mars. They will look at sunsets that fade from butterscotch to blue, feel the faint tug of gravity that makes every step a slow dance, and watch Earth rise as a distant, shimmering dot in the night sky. In that moment, the search for life will no longer be abstract. It will be personal. Humans will see the planet not just as a laboratory, but as a story, one that connects their own fragile existence to the vast, indifferent beauty of the cosmos. And when the first human voice echoes across that alien desert, it will carry with it all of Earth, every language, every question, every dream humanity ever dared to whisper into the stars. Question of life on Mars is not simply about microbes or fossils. It is about the boundaries of life itself. For centuries, humanity has sought to understand what it truly means to be alive. On Earth, life surrounds us in every possible form. In oceans, forests, deserts, and even in the most hostile environments. We have found microorganisms thriving in boiling hot springs, surviving inside nuclear reactors, and enduring the vacuum of space. Each discovery stretches the definition of life just a little further, making the question of what might exist on Mars both more complex and more compelling. If something ever lived there, even something microscopic, long dead, and frozen in rock, it would mean that life is not unique to Earth. It would mean the universe itself has a tendency toward living things, that life is not a rare spark, but a recurring melody written into the fabric of creation. Scientists have long debated how to define life. Is it metabolism, the ability to consume and convert energy? Is it reproduction, the capacity to copy itself and evolve? Or is it something subtler, pattern of organization that maintains itself against chaos? When we search for life on Mars, we carry with us these earthbound definitions, but Mars may not conform to them. The life that might have existed there could be based on chemistry utterly unfamiliar to us. Instead of relying on water, it might have used perchlorates or brines as a solvent. Instead of carbon, it might have structured itself around silicon or iron. If such life once arose and left behind traces that our instruments can barely interpret, would we even recognize it as alive? The challenge is not only to find evidence, but to understand it, to know when we are looking at something born of biology rather than geology. In recent years, the boundary between these two worlds, the biological and the chemical, has become increasingly blurred. On Earth, certain mineral formations, such as pyrite or stromatolites, can mimic the textures and patterns left by living organisms. Methane, one of the most intriguing gases detected in Mars' atmosphere, can be produced by both microbes and geological reactions. Organic molecules, the building blocks of life, can form spontaneously in the absence of biology. Each discovery on Mars, therefore, sits in a space of uncertainty, where science must weigh every possibility. When Perseverance detects organic carbon in ancient lakebeds, when orbiters measure fluctuating methane levels, the question is always the same. Are we witnessing the remnants of something alive, or the natural alchemy of a restless planet? If Mars does hold evidence of ancient life, the implications stretch far beyond science. It would mean that the universe, given the right conditions, naturally generates life wherever it can. It would suggest that the Milky Way may be filled with living worlds, perhaps not with civilizations, but with microbial ecosystems clinging to existence under alien suns. Such a discovery would transform biology into cosmology. It would shift humanity's view of itself from being the exception to being part of a pattern. Even the faintest fossilized bacterium on Mars would rewrite our cosmic story, forcing us to accept that we are not the center of life's narrative, but a single verse in a grander song, the philosophical and spiritual implications would be just as profound. Religions and philosophies throughout history have grappled with the idea of creation and purpose. To find life elsewhere, even simple life, would challenge centuries of human belief about what makes us special. It would invite new interpretations of existence, suggesting that life may be an inevitable expression of the universe's drive toward complexity. Scientists, theologians, and thinkers would need to reconsider what sacred means when life is not limited to Earth. Perhaps the divine, if one believes in it, would seem more expansive, woven through the galaxies themselves. And for those who see meaning in the cosmic order, the discovery of life on Mars might not diminish humanity's significance, but deepen it, connecting us to something vast and ongoing. Yet, even if Perseverance and its successors find no evidence of biology, that too would be a revelation. It would force us to confront the possibility that life, despite the apparent abundance of habitable conditions, may be exceedingly rare. Mars once had water, warmth, and chemistry, all the ingredients Earth possessed. If it remained barren, then perhaps something unique and fragile occurred here, on our blue planet, that the cosmos has not repeated elsewhere. That realization would make life not less meaningful, but infinitely more precious. It would underscore the responsibility that comes with being alive, to preserve, to protect, and to understand the singular gift of consciousness in a silent universe. In laboratories on Earth, scientists already attempt to simulate Martian conditions, recreating the chemistry of early Mars to see if organic molecules can form spontaneously. They study meteorites like Al-84001, searching for fossil-like shapes and isotopic patterns that hint at biology. They experiment with extremophiles, organisms capable of surviving in radiation and desiccation, to test whether they could endure the harsh climate of Mars. These efforts blur the line between exploration and introspection. In seeking life elsewhere, we inevitably study the origins of our own. Perhaps the story of Mars is not separate from Earth's, but part of a shared cosmic heritage. A tale of two planets that began together and diverged, one nurturing life, the other freezing in silence. As technology evolves, we may soon bring pieces of Mars back to Earth, real samples of rock and soil that could hold answers beyond imagination. In sterile, clean rooms, scientists will open those precious tubes with the caution of surgeons handling something sacred. If within them lies even a single microfossil, or a chemical signature undeniably biological, it would be the most significant discovery in human history. But if those samples contain no trace of life, that too will tell a story of resilience, of survival against odds, of how life on Earth flourished while its twin world faded. Either way, the question of Mars becomes a mirror, reflecting our own nature, our drive to understand what life truly means. And as we continue to search, our definitions may have to change. Perhaps life is not confined to cells or DNA, but includes any system capable of self-organization and adaptation. Perhaps there are forms of existence that are not biological, but informational, energetic, or even mineral. Mars may reveal that the boundary between the living and the non-living is far thinner than we imagine, that the essence of life is not a chemical recipe, but a universal pattern, an impulse toward complexity, persistence, and transformation. From the first glimmer of Martian canals seen through 19th century telescopes to the high-definition images captured by rovers today, our relationship with Mars has always been more than scientific. It has been emotional, almost mythic. The red planet has been our mirror, reflecting both our hopes and our fears. We have imagined civilizations there, sent our machines to its deserts, and dreamed of walking upon its dust. In every experiment, in every landing, there is an echo of something deeply human, the unrelenting desire to know whether we are alone. Each chapter in Mars exploration has pulled us closer to that answer. The Viking landers of the 1970s tested for life directly in the soil, igniting debates that continue to this day. The discovery of organic molecules by Curiosity, the fluctuating methane levels observed from orbit, and the intricate patterns of ancient riverbeds seen by Perseverance, All of these threads weave a story of a planet that once may have been alive, or at least alive with potential. And though we have yet to find a fossil, a spore, or even a single cell, we have found evidence of something just as powerful, that Mars was once capable of hosting life. What makes this quest extraordinary is not just the science, but the reflection it casts upon ourselves. In searching the stars for life, we have deepened our understanding of our own origins. We have learned that the ingredients for existence, water, carbon, energy, are not rare. They are scattered throughout the galaxy like seeds, waiting for the right soil. And perhaps, in some ancient epoch, Mars was one of those soils. The notion that life could have sparked there, even briefly, reshapes how we see the universe, not as a void, but as a canvas alive with possibility. The next steps will move beyond machines. Humans will one day walk the plains of Jezero crater, collect samples with their own hands, and gaze back at Earth, a pale blue dot hanging in the cold Martian sky. That moment will not just mark a technological triumph. It will be a spiritual one. For the first time, life from one planet will stand upon another, searching for traces of its cosmic kin. Whether we find that kin or not, we will have proven something essential about life itself. That it seeks, that it adapts, that it endures. Perhaps Mars will teach us that life is fragile and rare, a fleeting spark in an indifferent universe. Or perhaps it will reveal that life is universal, written into the chemistry of worlds, waiting only for time and sunlight to awaken it. Either answer will transform us, because in the end, the search for life on Mars has never been only about Mars. It has always been about us, about our hunger to connect, to understand, and to see in the endless darkness, not just emptiness, but the reflection of life itself, reaching out across the stars.